Hi folks, we're going to take a look at page 329, number 14. Okay, so here what this function gives us is the distance of a car based on how intense the headlights appear. Okay, so first thing that they ask us to do, pretty straightforward, is just to determine the distance when the intensity is 50 lumens. Okay, so let's just do that here. So we've got log of, now one thing I do want to bring up here is if your calculator does not open up the brackets automatically, you better make sure you put that in, especially when there's some kind of operation in your input. Okay, so here we have 50 divided by 125, okay, and times negative 167. Okay, so about 66.5. So that means car is 66.5 meters away if the intensity of the light is 50 lumens. So in question B, it asked us twice the intensity mean the car is only half the distance away, which seems to be reasonable. Okay, now if you have seen intensity of light in physics, you probably would guess that this is not the case. But let's see what happens here. So I'm just going to determine d at 100, so double the intensity. So I'm just going to do it explicitly here. So log of 100 over 125, and let's see what happens if we get something in the 33 meter range. Okay, so here we have log of 100 divided by 125 times negative 167, and that gives us about 16.2. Okay, so we see that it is not the case that just because the lights appear twice as intense that it means the car has traveled half the distance. Okay, so question is, what do we conclude by this? Well, it means that fog will play, and again, of course, this was with a car driving in fog, and basically the conclusion is, fog might play a bit of tricks with you. Okay, so if you start off and you have a certain intensity, at 66.5 meters away, okay, you might think that, well, hey, if the intensity is twice as bright, then they must be about 33 meters away. But of course, that's not the case. They're only about 16 meters away. Okay, so you might sort of think, well, how does this affect, somebody driving a car? You wouldn't be thinking about how intense the light is. However, think of a pilot with a plane needs to have a sense of how far it is away. And certainly the sensors would be using an equation like this to measure the intensity of the light and then figure out an approximation for how far the object is. Or think of a train, with two tracks. Train needs to know how much time it has if it needs to switch from one track to the other, and there might be a train coming in the other direction. It's important to know exactly how far away that train is. Okay, so beyond that, I do want to look at something else here. Okay, so in order to figure out what was going on, we actually used specific numbers. So we started with 50 meters, and then we started with 50 lumens, and then we changed the intensity to 100 lumens. But I just want to see what happens when we do this more generally. So let's say I start with, a given distance, okay, for a given intensity of light. So I'll call these I1 and D1. Okay. So now let's say I want to determine the distance when I double the intensity. Okay. But since I know that the intensity is going to be twice as much as the original, I'm just going to replace this by 2 times I1. Okay. And so now the question is can I do any algebra, okay, to rewrite this expression, okay, so that we've got this original expression in there, so we can make some sort of determination about the relationship between them. Okay. And hopefully you remember, hey, wait a minute, we do have something that we can use. Okay, and maybe if I rewrite this in a slightly different way, if you haven't thought of it yet, you'll now think of it. What if I rewrite this as 2 times I1 over 125? Okay, perfectly legal. Okay, these two things are exactly identical, but now hopefully you remember that, wait a minute, we have a principle for logarithms that says that the logarithm of a product is the sum of the logarithms. So this can be rewritten as negative 167, and this expression here can be rewritten as log of 2 plus log of I1 over 125. Okay, and so now we can just distribute the negative 167. Minus log of I1 over 125. And we see here that we're not multiplying the original expression. Oops, forgot the 167 here. We're not multiplying the original expression by a number. We're actually subtracting a number. Okay? One might have expected that we'd be multiplying the original distance by some number, but we're not. Okay? And in fact, let's calculate what negative 167 times log of 2 is equal to, and we see that it's about 50.3, or negative 50.3. Okay, which is exactly the difference that we found in our two answers earlier. But what's interesting here is that notice that it wasn't dependent at all on the original intensity. So that means if I had started with an intensity of 20 and then changed it to an intensity of 40, I would have still ended up with the exact same difference between the two distances. Okay, so again, an interesting property that comes from the fact that this logarithm of a product can be written as the sum of two logarithms. Okay, so that'll be it for now.